We give the University of Auckland permission to use this video for the purpose of teaching other Part 1 Engineering 1-to-1 students. Our first experiment is finding the friction coefficient between our 1-to-1 course book and a coin using the spring of a pen.
Hello, today I'm gonna find the friction coefficient of this one-to-one course book by using this pen's like power. First, I'm gonna use this book stand to find this pen's spring force, and I will find this part of friction coefficient by using this pen. Thank you. I know mass theta, gravity, and time taken, and length of this long. So I use one equation, and I found the acceleration of this object to go onto here. And I found the F of net force, and I can know like mg, and I know F normal force and mg sine theta, and using mg sine theta and net force, I found the friction force, and I find the friction force, and using friction force and normal force, I found the friction coefficient. This is the process finding force by pen. These are the things that I know, and I can find final velocity by using this equation, and using this equation I can find acceleration. And from this diagram, I can find net force, and I can find friction force too by using like friction coefficient and normal force. Therefore, I can find force by pen, and this force by pen is, oh my god, I forgot to write Newton. Yep, this is the force by pen. This is our last process, finding one-to-one course book's friction coefficient using pen spring force. Yeah, I know these things, and I can find final velocity, and I can find accelerations. And from this diagram, I can find net force, and I know the pen force, and finally the friction force is this one in one-to-one course book. Therefore, we can find friction coefficient of one-to-one course book, and this is the friction coefficient of one-to-one course book.
Our next experiment is measuring the tension force of the supporting ropes of a crane. To model a crane, we are using a tent pole and a piece of rope attached to the ground at two different pegs. To keep the tension force equal, we are using a pulley system at the top of the tent pole, and to measure the tension force, we are using a baggage scale. Okay, this is our home experiment, and the aim of this is to model the process of a crane. We have a tent pole which weighs exactly 1 kg at 1 meter distance, supported by two pieces of string that are 1 meter apart, the center of the pole being centered down the middle, and the pole is at an angle of 45 degrees. It's a bit hard to see here, but what I have here is a bag weighing device which I have attached to the string to show us the tension force in the string, which this device shows us to be 0.48 kgs. Let's see how accurate this device really is. Now this is test number 2, where we are using an angle of 30 degrees. And as you can see, the tension in the rope has increased to 0.61 kgs. And now lastly, we are testing 60 degrees, which is giving us a tension force of 0.5 kgs. Here's a demonstration to show you how we took our measurements. Taking the angle using a protractor. The ruler showing us that our pegs are 1 meter apart. And from the center, we are also 1 meter towards the middle. Let's have a look at what we did to test our experimental results. We looked at the experiment from the side in 2 dimensions, splitting the experiment into 2 triangles. The larger one with an angle alpha between the rope and the ground, and the smaller one with an angle theta between the tent pole and the ground. We can write angle alpha as a function of theta as the tan inverse of 2 sine theta over 1 plus 2 cos theta. Now, using that angle and the triangle that is created, we can apply our sum of moments in equilibrium equals to 0 equation, and we get a general solution which is quite long, and I won't read it out now. It involves a lot of different angles, and yeah. So afterwards, we plug in all of our numbers into this general solution for our tension force in the rope, T1. But then we have to divide that value by 2, because remember, we are only looking at it from the side, and at the top of our tent pole is a pulley. So after we divide the values that we got for the various angles of theta by 2, we get our tension force in the rope. Now after we've gotten that, we can find what our reactant forces on the ground exerted by the actual tent pole also are, using the sum of forces is equal to 0 for equilibrium case. As you can see, when comparing the theoretical to the experimental results of our experiment, they're quite different, which is a bit of a shame. Our conclusion from this is that the baggage scale that we used is not very accurate when testing at low forces. We're really talking about like 0.5 of a kg. If we had the time, we would redo this experiment and add another weight, maybe another 2 kgs, at the top of the tent pole in order to test with some higher stresses and to see if we get any more consistent results.